Welcome to lesson number 10, Navigation. Your in-class instructor is Josh Perzek. Now, in this lesson, you'll learn how to use and understand the instruments in your aircraft designed for navigation. We will cover VOR facilities, VOR navigation, VOT procedures, ADF equipment, NDB navigation, and GPS navigation. Now, these instruments and systems are there to help you navigate your flight plan and are invaluable if you ever become lost while flying. Let's join Josh now in the classroom for navigation.
We'll start with VOR navigation and the VOR indicator you will find in your aircraft. Now, the VOR ground-based station transmits a unique signal which is received by your aircraft's VOR receiver. The transmitter projects a signal 360 degrees around the station, and you can see that right here. These signals are referred to as radials from the VOR transmitting station. To understand this concept, think of a hub of a wheel and the wheel spokes, or in this case, the radials. Here they are projecting outward from the hub. You can see that right here. Now, the VOR radials are all considered to be from the station. Here's the VOR station, or the hub of the wheel, right here at the center. Now, in addition to the VOR indicator, the aircraft is equipped with a receiver. Now, the receiver is a tuning device. Prior to navigating to or from your VOR station, you have to enter the VOR frequency and identify each station. Each station has its own Morse code identifier. Now, here's an example of what you hear when you identify the station.
Pilot weather reports are requested. Contact Flight Watch or Flight Service as appropriate for additional details.
Here's the VOR indicator that you will find in your airplane, shown right here. This little knob is called the OBS. You can see that right down here, or the Omni Bearing Selector or Course Selector. The Omni Bearing Selector can move the entire face or the entire dial of the instrument to any desired course, or it can determine a radial from which the aircraft is flying. Remember, radials are magnetic bearings outbound from the VOR ground station. Now, this is the Course Deviation Indicator, or CDI as it's referred to. It indicates the displacement of the aircraft relative to the selected Omni bearing. Now, if the CDI needle moves to the left, you're to the right of your desired course, and you would fly left to intercept it. Now, each dot that you see on the needle right here represents 2 degrees. When the needle is centered, you're directly on the selected course, like we see right here. Now, this window right here is the to from indicator flag. If it displays 2, as in this case right here, you see it displaying 2, then you are flying to the VOR station. Now, if from is displayed and the course is shown at the top is followed, the aircraft is flying away from the VOR station. The window can also show a red flag, which indicates that the unit is off, and that's what we have in this case that you see right here. Now, the little red flag is popped up. This means you are in an area of ambiguity where the VOR signal cannot be relied upon. Now, we'll go into more detail on this shortly. Assuming you are directly south of the VOR station flying north with the OBS set to 360 degrees, the needle is centered, and you can see that right here. Now, if you set the OBS to 330 degrees, the needle is deflected to the right. And we see that in this example right here, so you can intercept the 330 degree radial. When you set the OBS to 030 degrees, the needle deflects to the left, so you can intercept the 030 degree radial. Now, let's put this concept into motion. First, we'll set the OBS to 330 degrees, and when we do, note the needle deflection. Next, we'll set the OBS to 030 degrees, and again, note the needle deflection. Now, this next animation illustrates the operation of the to and from flag. Again, we are directly south of the VOR station, flying north. Note the needle is centered, and we have a solid to indication. Next, if we set the OBS to 180 degrees south, note how the needle deflects. You'll also see a brief red nav flag, and finally you'll see a solid from indication with the needle again centered. Let's watch that one more time and watch for the red nav flag as the OBS is swung from 360 degrees to 180 degrees south. Now these concepts will become clearer as we continue in this lesson.
Now that we have a basic understanding of the VOR transmitter and receiving equipment, let's apply this knowledge to VOR navigation using charts and hypothetical examples. Remember, all aeronautical charts contain ground-based navigational aid depiction, and the FAA will test your knowledge, understanding, and application during flight planning and in the cockpit. Let's go back now to the classroom and Josh.
If you check an aeronautical chart, you can see how a VOR and its radials are depicted. To find the VOR frequency, look in the upper right-hand corner of the VOR transmitter, like you see right here, and here's a close-up of that right down here. Now, you can see here we have the Elizabeth City blue navigation box, and in this instance, our VOR frequency for Elizabeth City is 112.5. The VOR symbol is usually shown in the center of the compass rose, like you see right here, unless the VOR is on the airport surface. Then the airport symbol will be at the center of the compass rose. Now, if you drew a line projecting outward from the center, you could see each and every radial. Now, refer to the chart legend to help decipher these symbols. This legend is provided to you during the knowledge test. Now, let's go back to the Elizabeth City VOR and view the 090 degree radial. Here's the airport right at the center, and here's the VOR with the 090 degree radial projecting outwards. Now, here's the 340 degree radial right here projecting outwards, and so on and so forth. If you could imagine all the radials, you would see how this would form the spokes of a wheel. Now, courses are to the station, and radials are always from the station. Now let's talk about Victor Airways. There are established Victor Airways, and you can see a close-up of a Victor Airway right here. Victor Airways always run between VORs. These are identified on sectional charts by blue lines with the airway number following the letter V. Class E airspace on these Victor Airways starts at 1,200 feet above ground level and goes up to, but does not include, 18,000 feet MSL. Now, Victor Airways are 4 nautical miles wide on either side of the airway centerline, or 8 nautical miles across. Now, you should exercise caution when flying where airways converge and always maintain continuous visual scanning for other traffic. To determine your position in relation to one or more VOR stations, first tune and identify the selected stations. Next, rotate the OBS until the CDI centers with a from indication. The OBS reading is the magnetic course from the VOR station of the aircraft. Repeat this procedure using a second VOR frequency. Then the aircraft is located at the point where these two lines intersect, as you can see right here. Here's an example of navigating to the VOR. Suppose you want to fly to the VOR station and you want to fly on that same 240 degree radial. The OBS would be set to the reciprocal of 240 degrees with a 2 indication. The reciprocal is 060 degrees. You are still on the 240 degree radial, but your VOR indicator will be set to 060 degrees. Let's fly from a VOR station outbound. Right here is the compass rose, and here is the 270 degree radial, here's the 180 degree radial, and so on and so forth. In the center is the VOR. Now over here is the VOR indicator, and the 240 degree radial is selected with the airplane flying from the station. We are flying out from the station indicating from on the VOR indicator. If we fly 240 degrees and we have 240 set in the VOR indicator with the needle centered, we are flying out directly over the 240 degree radial from the VOR station. Your compass heading should match this 240 degree radial as well. This animation illustrates intercepting and following the CDI needle. Here is the Elizabeth City VOR shown right here. Our intended course is the 270 degree radial. Now we'll put the aircraft in motion and note what happens. As the aircraft intercepts the 270 degree radial, the needle centers. Also note the to and from indications as the aircraft overflies the VOR station. It changes from to from. We'll run the animation again. Go ahead and check it out. You'll see the needle center as the aircraft approaches the course. As it flies over the station, note the change from to from on the to from flag. One of the important oddities of VOR navigation is known as the area of ambiguity. Check the Sulphur Springs VOR. This is our intended course, about 060 degrees. If we bisect the VOR perpendicular to our course and note the to and from quadrants, we get a to indication on any radial east of the red bisection line as we approach the VOR from the west. Note as we fly directly over the VOR, the signal becomes unreliable or ambiguous. When approaching a VOR ground station, the CDI needle will become more and more sensitive and may deflect from side to side. Let's run the animation again. When passing directly over the station, the flag will also change from to from. The red nav flag may flicker in and out of view because this signal is unusable at such a close range. The CDI needle will then show a full-scale deflection, and in this area you will get an off flag.
A few test questions will ask you to identify your position using VOR navigation. Let's try one of these now. The VOR receiver has the indications shown. What is the aircraft position relative to the station? A, B, or C? Okay. Now, look at the number 1 VOR indicator. The OBS is set for 030 degrees. The to from indicator says you're heading to the VOR station. Remember, you're flying the radial, which is going to be the reciprocal of 030 or 210. It is the opposite of what is dialed in at the top of the OBS here. The reciprocal is shown at the bottom of the indicator. In this instance, it puts us south or southwest of the station. The CDI needle is deflected to the left, which means you have to fly to the left to intercept the 210 degree radial. In other words, the airplane is right of the selected course. Now, since you're to the right of 210 degrees, you have to be to the south. So, C is the correct answer. In some instances, you may be asked to identify 2 VORs, or your position from 2 separate VORs. To do this, you simply perform a cross-check. Let's do another FAA test question. What is the approximate position of the aircraft if the VOR receivers indicate the 245 degree radial from Sulphur Springs, VOR, DME, and the 140 degree radial or 140 degree radial from the Bonham Vortac? It's one A, B, or C, one correct answer. First, let's find the VORs. Here's the 245 degree radial out from Sulphur Springs, and here's the 140 degree radial out from Bonham Vortac. Notice the intersection of these two radials. Here's the Glen Mar Airport. The correct answer should be B. You're closest to the Glen Mar Airport. Okay, next up, VOR test procedures. Back to the classroom with Josh.
VORs also have to be periodically checked for accuracy. One method to do this is to use a VOR test station called a VOT. Airports using VOTs can be found in the Airport Facilities Directory. To use this service, tune your nav radio to the frequency listed and listen to the Morse code identifier. Then center the CDI by tuning the OBS. The OBS should read 360 degrees from or 180 degrees to. There is an acceptable error of plus or minus 4 degrees with these readings to still be considered usable. A helpful mnemonic to aid in you remembering how to use the VOR test frequency is to remember Cessna 182. Here's what we mean. Center the needle, C for Cessna, 180, turn the OBS to 180, and 2 equals a 2 indication.
Electronic navigation equipment has a rich history dating back more than 80 years. One of the classic and most enduring navigation aids is the Automatic Direction Finder, or ADF. While GPS navigation may have overtaken much of today's navigation function, The ADF is still installed in many airplanes. While some pilots appreciate their superior AM radio reception capability in flight, they still make excellent navigation tools. And besides, the FAA still expects you to understand this vintage equipment. Okay, let's move along to ADF equipment in the classroom.
We'll move on to discuss navigation using the ADF indicator. ADF stands for Automatic Direction Finder, which is the name of the instrument in your airplane. The system consists of an indicator and a receiver. The ADF indicator has a needle that points to a ground station called a non-directional beacon, or an NDB. Refer to the chart legend for NDB symbols. The legend will be available to you during the FAA knowledge test. Let's check this graphic. Here is the non-directional beacon, or NDB, ground control station. The red arrow depicts the aircraft flight direction. No matter which way you tune the airplane, the needle always points towards the station. As the aircraft heads south, the needle points to the NDB. Here's the aircraft again heading north, and the needle again points to the NDB. Here it is heading northeast, and note that the needle again points to the station. This time it's heading southwest, and the needle points to the NDB. In the last example, it's heading northeast, and the needle again dutifully points to the station. Let's put this concept into motion. Note as the airplane traverses from west to east, north of the NDB ground station, the ADF needle dutifully points to the station. In this next example, the airplane is tracking from the southeast to the northwest. Again, the ADF needle points to the station. The ADF may be used to home or track to a station. Homing is flying the aircraft on any heading required to keep the azimuth needle pointing directly in front of the aircraft until the station is reached. Tracking involves following a straight geographic path by establishing a heading that will maintain the desired track over the ground regardless of wind effect. There are three types of ADF indicators. Some have an adjustable card ADF indicator, and with these the magnetic compass heading can be set on the ADF indicator, and the bearing to the station can be read directly under the needle pointer. Others have what's called a fixed card, where north is always at the top and 180 degrees is always down at the bottom. With these, the bearing to the station requires some computation. Alternatively, the ADF indicator could have a rotating compass card integrated with a VOR indicator. This instrument is called a radiomagnetic indicator, or an RMI. The RMI allows the pilot to read the magnetic heading off the aircraft directly without referring to another instrument. It's important for you to know what kind of ADF indicator is in the aircraft you're flying. Relative bearing is the number of degrees a pilot has to turn the airplane to the right to fly directly to the station when using a fixed card ADF. There is a simple calculation using the relative bearing to help you determine the magnetic bearing to the station, which is the magnetic course to fly direct to the station. Here's the formula. Relative bearing plus the magnetic heading of your aircraft equals the magnetic bearing to the station. Here are some examples showing 4 fixed card ADFs. The FAA knowledge exam will test your knowledge of relative bearings to the station. If they don't give you a magnetic bearing, you can simply figure relative bearings to the station by looking at the head of the needle. Notice indicator number 1. The relative bearing to the station is 315 degrees. That's the number of degrees you'll have to turn to the right to get to the station. Now notice indicator number 5, and it shows the relative bearing to the station of 360 degrees. To find a magnetic bearing to the station using a fixed card ADF, you will be given a magnetic heading, say 320 degrees. Write down the relative bearing to the station found on the head of the needle. In this case, it is 225 degrees. From here, it's simply arithmetic using our formula. Here's how to calculate the magnetic bearing to the station. The given magnetic heading is 320 degrees. The head of the needle indicates a relative bearing of 225 degrees. Adding these two values provides a magnetic bearing to the station of 545 degrees. But wait a second, that's greater than 360 degrees. To normalize the magnetic bearing to the station, we must subtract 360 from 545. In this case, this equals 185 degrees, as you can see right there, which is the magnetic bearing to the station. Besides a fixed card ADF, some airplanes have a movable card ADF or RMI. Here's what one looks like. Now, the reason we call it a movable card is because the card moves around, and it's done so by adjusting the set knob that you see right here. The nice thing about having a movable ADF is that finding the magnetic bearing to the station is already presented to you. This compass card will rotate. You adjust this with your magnetic heading, and you automatically have your magnetic bearing to the station. Check this example. Here the aircraft has just completed a turn from 020 to a new heading of 315 degrees. With this adjustable card ADF, you set your new magnetic heading of 350 degrees using the set knob right here. Since the needle always points to the ADF, the bearing to the station under the heading of the needle indicates 190 degrees. The tail of the needle is the reciprocal 180 degrees opposite, or in this instance, it's 010 degrees, as you can see right here. In some instances, you still need to know the relative bearing to the station. Here's the formula. Add the magnetic heading to the magnetic bearing to find the relative bearing to the station. Here's how it works. Take the magnetic bearing of 190 degrees and subtract the magnetic heading of 315 degrees. Our answer is negative 125 degrees. You can't have a negative heading, so we need to normalize by adding 360 degrees. Now we can see that our answer is 235 degrees right turn. Remember this right turn relative bearing. Always turn to the right to get your relative bearing. Here are some more examples of a movable card ADF. Here's our magnetic heading of 330 degrees shown right here at the top. Our bearing to the station, our magnetic bearing to the station, is at 210 degrees, and the reciprocal is 030 degrees. Here's another example. Here's 315 degrees magnetic heading. Our magnetic bearing to the station is then 190 degrees, and the reciprocal is 010 degrees. Now, from time to time, you're going to be asked to fly an intercept to a magnetic bearing. Let's say, for instance, you want to intercept the 180 degree bearing to the station. Here are the givens involved. You have a magnetic heading of 315 degrees. To fly an ADF intercept, you typically use about a 45 degree interception course. So adding the intercept angle of 45 degrees to our intercept bearing of 180 degrees gives us an intercept course of 225 degrees that you can see right here. Notice one of the nice things about this movable card ADF. See these little triangular ticks all the way around the dial? You can see them right here. These are placed at 45 degree intervals, or our typical 45 degree intercept angle. The next graphic illustrates what we just learned. We wish to intercept the 180 degree bearing to the station. We are flying a compass heading of 315 degrees. Step number 1, turn the airplane to 225 degrees. Step number 2, reset your movable card ADF to show a magnetic heading of 225 degrees. Step number 3, as the head of the needle begins to turn toward the 180 bearing to the station, we slowly turn to intercept a course of 180 degrees, and we no longer have an intercept angle. What you have done is intercepted the 180 degree bearing directly to the station. Now, that ends our concepts on ADF and NDB navigation.
Let's apply what we've learned to an FAA test question. Which ADF indication represents the aircraft tracking to the station with a right crosswind? A, B, or C? And here are the choices. 1, 2, 3, and 4. Now, it's seldom, if ever, that you'll navigate on a bearing or a radial without having to correct for some type of wind drift. When you're tracking on an NDB with no wind, the needle is going to point straight up. Let's say you drift off course to the left, pushed there by a right crosswind. Once you're on course, you have to apply a wind drift correction. The needle points in the opposite direction by a corresponding number of degrees, requiring a correction. Say you apply a 20-degree wind correction angle to the right, and this keeps you on course. Your needle is going to be deflected 20 degrees in the opposite direction, or in this case, off to the left. Remember this phrase, opposite angles are going to be equal. A typical wind drift could be anywhere from 5 to 30 degrees. The needle will point to the left with a right crosswind. Look at the choices and find out which one is going to be closest to what you need. Here is ADF indicator number 1. You can see that the deflection is more than 5 to 30 degrees. Look at ADF indication number 2. Once again, it points to the left, but way outside our 5 to 30 degree correction angle. Here's ADF indication number 3. It's a possibility. It has a smaller correction angle. The tail of the needle points to the left, but the head of the needle points to the right. Remember, we have to fly to the right, so we're going to get a left indication on our ADF needle. You can rule this one out. That leaves number 4. Here's the needle pointing off to the left, which means we're flying to the right to compensate for that crosswind. It's a small enough angle that it could be between our 5 and 30 degrees. Now these are our 4 choices. Number 4 seems to be the best bet, and number 4 is one of our choices. Which ADF indication represents the aircraft tracking to the station with a right crosswind? Well, that's C, the number 4. Now, this final topic in this lesson is a new concept, GPS navigation, which stands for Global Positioning System. Now, do you think that, for instance, a handheld GPS is kind of a good solution for a VFR pilot who's really wants some cockpit automation?
Yeah, absolutely. The navigation computer really is the heart of the cockpit, and these VFR-only handheld units really do offer a lot of features. You've got your GPS navigation, your moving map display, and in some cases, weather. So this is an excellent way for a VFR pilot to get many of the capabilities offered in an IFR-capable ship.
Now, Steve, you've probably got some recommendations to pilots, ways to automate their current cockpit. What would you recommend?
Well, for the pilot that's adding one system at a time to their cockpit, I would just say start out slowly. Take the time to get to know each system, how it works, and how to integrate it into your everyday way of doing things.
Now, as a pilot, what instrument would you be most interested in adding to the traditional aircraft? Yeah.
I think the typical first choice is the GPS computer and a moving map display. From then, many pilots are interested in the benefits of a traffic collision avoidance system or getting real-time weather information in the cockpit also. So any of these are available.
Now, GPS uses a constellation of 24 satellites that are orbiting in space. Let's go back to the classroom right now.
These satellites broadcast a signal. Each satellite transmits a position signal. A GPS receiver located in your airplane computes the aircraft position based on these signals. A minimum of 3 satellites are required for lateral navigation. When a GPS receiver is able to receive the signal from at least 3 satellites, it is able to accurately calculate its position based on the principle of triangulation. The GPS receiver uses data from a minimum of 4 satellites to yield a 3-dimensional position, latitude, longitude, and altitude, and a time solution. GPS systems are now installed in almost all new aircraft. These installations are called glass panel installations. For example, on this aircraft, you'll notice a complete integration of navigation, flight instruments, and performance instruments in one complete system. On some aircraft, GPS systems are integrated with a traditional classic instrument stack. On this installation, a partial glass panel provides a moving map and GPS position depiction. However, classic flight and performance instruments are still used in the instrument panel. Either way, GPS accuracy is far superior to VOR and ADF navigation. An aircraft navigating by VOR or ADF is limited by the location and range of those ground-based stations. You may not be able to navigate by the shortest possible route because of, for example, some mountains could be in the way. They could block a VOR signal, but GPS allows us to navigate direct because the signal comes from space and it's not limited by the ground-based transmitters. Here is a typical moving map and GPS installation. It uses a 24 satellite constellation. 3 satellites are required for a lateral fix and 4 satellites are required for a 3D fix. Finally, GPS provides complete global coverage. When navigating by GPS, your GPS equipment will monitor the strength and signal it receives to determine if it's good enough to be used for navigation. Because of these satellites, they may occasionally be blocked by the curvature of the Earth or by portions of the aircraft structure. So you should be aware of something called a RAIM warning. RAIM stands for Random Autonomous Integrity Monitoring and alerts us when the signals may be too weak to be used. In this warning, it appears on your GPS, and if it does, select an alternative means of navigation until the RAIM warning disappears. To use GPS for navigation, you would select the Direct To key on the face of the receiver, and you can see that right here. Normally this key will look like the letter D with an arrow through it. After selecting this button, enter the airport identifier or navigational aid you want to go to. For airports with alphabetic identifiers, it is necessary to first input the letter K. Now note that this is only necessary when navigating towards an airport. If the identifier, say, is for the Newburgh VOR, in this case UBG, you don't have to use a K. You just enter UBG because Newburgh is not an airport. Once the desired waypoint is selected, simply navigate by keeping the needle centered on your OBS. If your GPS is coupled with the OBS indicator or by tracking the desired track as shown on the face of the receiver. The GPS is also going to show your ground speed, distance to the waypoint, and the estimated time of arrival at the waypoint. A waypoint is a predetermined position usually specified by latitude and longitude.
How do you see land-based tools fitting into today's big picture with the availability of Google Earth and GPS so widely available?
Well, I don't see ground-based navigation going away anytime soon, and I think it's going to continue to be a valuable resource, both as a backup means of navigation and also as a means of training pilots to develop spatialization skills.
Great. Well, how do you see the ideal scenario for pilots today, combining navigation by pilotage and dead reckoning with electronic nav aids?
Well, I think the important thing here is to always have a second means of navigation going on, even if it's only in your mind. So when flying along an airway using GPS, I'll do a rough calculation of how much time it's going to take me to hit my next waypoint. That way I know if I type something wrong into the computer, I'm going to know when I get there. The other thing is using backup navigation techniques really can help increase your awareness. We did a study at NASA, took 2 groups of pilots. One group used GPS and just flew as they will. Another group used GPS and was asked to point out landmarks on the ground as we made our way across the flight. And what happened was, at the end of the flight, when we turned off everybody's GPS computers, the people that were providing the landmark information actually had a better awareness than the people who were just relying solely on the GPS.
And now for our final FAA test question for navigation. How many GPS satellites are required to yield a 3-dimensional position, latitude, longitude, and altitude, and time solution? How many satellites, A, B, or C? Well, the correct answer is 4. C. The GPS receiver uses data from a minimum of 4 satellites to yield a 3-dimensional position, latitude, longitude, and altitude, and time solution. What are your suggestions for how pilots can manage the workload?
Well, the best advice I can give in regards to workload is get things done early, whenever possible, preferably on the ground. I like to think about all the scenarios that I might possibly get hit with that day and have a plan worked out for each and every one of them. You don't ever want to get to your destination airport, find out the weather is bad, and have it occur to you the first time that you might be going somewhere else. The thing that we have to remember here, the difference between airline flying and the kind of flying that we're doing here, is that Those folks have 2 pilots in the cockpit, and with us, it's just us. We've got to do it all ourselves.
Now, Steve, the audience may not know you've written a couple of very helpful books, one called Cockpit Automation, the other Modern Airline Cockpit. Tell us about those books.
Well, what we're trying to do here is to help make a smooth transition from the conventional style cockpit to the more modern glass cockpit. And it certainly is going to be a challenge, and it'll take a while for the FAA to integrate relevant topics into the knowledge tests, the practical test standards, and whatnot. But for now, we certainly need some material out there for pilots to read and familiarize themselves with the equipment before they step in the airplane for the first time.
Well, Steve, we certainly appreciate your being with us. Dr. Kastner, once again, and hope to have you back in future programs.
Oh, thanks. I appreciate it.
Great. Now, back to our instructors.
I'm Josh Prusik, and it's my pleasure to have been your instructor for this course. I hope you learned a lot and enjoyed your lesson on navigation.
We would like to thank Josh for all his fine work on navigation. Our final topic, number 11, communications, when you're ready.